All right, here we have two sets of points in the complex plane that are defined by S, which is the modulus of Z equals 3, and T, which is 2 times the real part of Z minus the imaginary part of Z equals K. And we need to determine the values of K for which T is tangent to S. Now, both of these equations don't look familiar at all. However, if we follow our process and make Z equal to X plus YI, hopefully once we've actually worked through them and got them into Cartesian form, we'll be able to identify what these two equations are that we're working with and continue from there. Another clue here is that the word tangent tells you that the one is just touching the other one in one point. And you'll remember from methods that when you are working with numbers of solutions, we always work with the discriminant, and with one solution or tangent, your discriminant is equal to 0. All right, so let's have a look. Let's let Z equal X plus YI. And what we've got is we've got the modulus of Z is equal to 3. And so X plus YI modulus is equal to 3. And remember, in order to find the modulus, what we need to do is say the square root of X squared plus Y squared is equal to 3. And that then looks very much like X squared plus Y squared is equal to 3 squared. And that's pretty cool. That's a circle with a center at 0, 0. Okay, so this is a circle in the form X minus H all squared plus Y minus K all squared is R squared. We recognize that. And so my center will be at 0, 0. And my radius is equal to 3. All right, so that's not too bad. Now let's have a look at the other one that said, well, we've got 2 times the real part of Z minus the imaginary part of Z is equal to K. Okay, so my Z is equal to X plus YI. So that means I've got 2X minus Y is equal to K. Okay. And that means that Y is going to be equal to 2X minus K. Now, what does that look like? Well, that to me looks like a linear function. Okay, so that's going to be linear in the form Y is mx plus c. So we've got our gradient is equal to 2, and our y-intercept, we don't know what that is. That's what we're trying to find out. It's going to be at 0 and negative k. All right, now, the cool thing about this is what we've got is we've got one equation here, and we've got another equation here. And in order to figure out how many times they intersect each other, I'm going to need to solve simultaneously. Okay, so for points of intersection, we're going to have substitute 1 into 2, or 2 into 1 actually. So that we're going to have, let's make that 2 into 1, so that's what we're actually doing. We've got x squared plus, now y is 2x minus k squared is equal to 3 squared. And so I've got x squared plus 4x squared minus 4xk plus k squared is equal to 9. And I'm going to bring it over so that I've got 5x squared minus 4xk plus k squared minus 9 equals 0. Now what I want you to notice is that this is actually a quadratic, okay? I've got an x squared there, I've got an x there, and this whole k squared minus 9 is my constant term. So this is in the form of ax squared plus bx equals 0. And as soon as it's in a quadratic form, well, that gives me the opportunity to use my discriminant. So in this case, my a is 5, my b is going to be negative 4k, and my c is going to be k squared minus 9. Just be careful when you're working with this that you get the right values. Okay, now for one solution, or tangent, delta is equal 0, and you'll remember that b squared minus 4ac is my delta. And in this case, my b squared is minus 4k times 5 times k squared minus 9 must equal 0. So I have 16k squared minus 20k squared plus, 2 9s are 1880 equals 0. And I can work through with that so that I've got negative 4k squared is equal to negative 180. So k squared will be positive 45 and k will be plus or minus 3, oopsie, not root 3, root 5. Okay.